Welcome to the Bad Mofo Show. I'm your host, Bad Mo Fogarty, and today we're going to continue with part 2 of resistance and resistors. Let's get started. I left off with talking about resistor identification. Now I'd like to pick up with verifying a resistor's actual ohmic value. Here's that color code chart again in case you'd like to play along. Now let's look at a few examples. The first resistor we'll look at is this. Looks like a red band followed by another red band, followed by a brown band, followed by a gold band. According to the color code, that's a 2 and a 2 with a multiplier of 10 and a gold band for plus or minus 5% tolerance. So 22 times 10 is 220 with plus or minus 5% tolerance. Don't be afraid to get out a calculator now. This video isn't about testing your math skills. And don't feel bad if you can't read the color codes on this little bugger without a magnifying glass, because I can't see it either. So 5% of 220 is 11. Therefore, I should expect the actual value of this resistor to be from 209 to 231 ohms. Now some of you are probably thinking the same thing I thought when I first started studying this material. That seems like an awfully big margin of allowable error. The fact is that many electronic devices can tolerate such margins and will operate just fine even if the actual current doesn't quite match the target current. And in the case of devices that do require more precise amounts of current, there are resistors that provide tighter tolerances. Let's check another resistor. This one looks like an orange band, followed by an orange band, followed by a brown band, followed by a gold band. So that's 33 with a multiplier of 10 with plus or minus 5% tolerance. 33 times 10 is 330, so with 5% in either direction, I should expect the value to be from 314.5 to 346.5 ohms. What about this one? Looks like a brown band, followed by a black band, followed by a red band, followed by a gold band. Did you beat me to it? That's 10 with a multiplier of 100. So we have a 1000 ohm resistor with plus or minus 5% tolerance. The value of this resistor should be from 950 to 1050 ohms. An easier way to check the value of a resistor is to simply check it with a multimeter. Oh look! They thought of everything. So with the multimeter set to the resistance setting, notated by the omega symbol, I just grab the ends of the resistor with my multimeter leads, and presto! As you can see, the actual value of this 220 ohm resistor is 217.4 ohms, which falls well within the specified tolerance. Now this method is only viable if you are reasonably sure that the resistor is either brand new or at the very least not damaged or defective. Also, to get an accurate reading on a resistor with a multimeter, the resistor must be isolated from the circuit. If the resistor is not isolated, the multimeter can measure the resistance of other components in the circuit and give an inaccurate reading. I'm also using these special leads for my multimeter to clip onto the ends of the resistor to remove any possible error due to my skin potentially making contact with the circuit and affecting the measurement. Let's check those other two, shall we? This 330 ohm resistor is actually 324.1 ohms, also well within the specified tolerance. And the 1000 ohm resistor looks like 0.988 k ohms. Notice the little K up here in the meter display? That's K for kilo, or increment of thousands. So 0.988 k ohms equates to 988 ohms, again, well within the specified tolerance. So now what? Let's build some simple circuits, make some measurements, and see how Ohm's law stacks up. What I have here is commonly called a breadboard, named so because in the days of electronics old, people would literally put nails or screws into a wooden bread cutting board from their kitchens for use as a semi-permanent circuit builder. Some folks even say that it half-ass resembles a piece of bread. Delicious. So how this thing works is pretty simple. You'll notice that it's full of little holes. This board is set up so you can insert electronic components and isolate them from each other and connect power to the circuit for the purposes of testing like we are about to do. Let's first examine the central portion and ignore the outer two columns of holes on either side that are outlined in blue and red. There are two main banks of holes, one on the left and one on the right, separated by a channel down the center of the board. Each bank has columns of 5 holes labeled A, B, C, D, and E, F, G, H, I, and J. You'll also notice that the columns make rows of 5 holes per bank labeled 1 through 63. Consider a single row of 5 holes. By designing the breadboard, those 5 holes are electrically common via a strip of metal built into the board. The same can be said for all of the rows in both banks, and the rows are independent from one another. This makes it possible to connect components of a circuit by routing from one row to another via the components themselves or a jumper wire. Now consider the outer two columns on either side of the board. Notice that on each side, one is outlined blue and is designated negative, while the other is outlined red and is designated positive. These columns serve as power buses and are constructed similarly to the columns in the center, except that all of the segments of 5 holes in each column are connected. This allows for power to be applied from the routed circuit from various positions on the board. There's more to breadboards than this, but I'll dive in a little deeper later when it becomes relevant. It also needs to be noted that this is a cheap breadboard and not a precision instrument. I'll prove that here in a minute. This little handy dandy is not the device you saw in the previous video, however it is made by the same company. This multimeter can measure current. I bought this one new for $135, used ones sell for less, obviously. Now don't think you have to go out and buy one of these. This multimeter isn't really necessary for everyone to have, but if you happen to be an electronics technician, you probably have one in your tool library. I bought this one because I love tools, and with it I can demonstrate Ohm's law for the purposes of this video. Now that we have a place to build our circuit, some resistors, and some measuring equipment, we just need a source of power. This is a 30 volt 10 ampere digital DC power supply. It has controllable voltage and current. I bought it brand new for about $75, which is on the lower end as far as quality equipment goes, but it should be good enough for this demonstration. There are other models which are higher quality, but with higher quality comes higher price. If I was doing electronics for a living, there wouldn't be any question, but the projected use frequency for it in my case did not justify the purchase. Well, here's the big bonus you've all been waiting for. Time to get into the meat and potatoes of this video. Let's build a circuit. So for our first experiment, you'll notice that I've already taken the liberty of inserting jumpers into the breadboard. This configuration will stay the same for all the experiments in this video, save for the different resistors and a couple more changes we'll talk about in a little bit. Now, I'll insert the 220 ohm resistor with one lead in row 5 and the other in row 12. This position isn't critical so long as no other lead is inserted into its row, save for the jumper. This is because in order to measure the current in the circuit, I need to make the ammeter part of the circuit. So I've clipped the negative lead of my meter here and the positive lead of my meter here. The only two open leads now are the ones attached to the negative bus and the positive bus on the breadboard. So let's verify our connections. Following electron flow theory, we should have current flowing through this jumper into the negative bus, then through the negative bus, through this jumper, over to row 5, through row 5 to the first lead of the resistor, through the resistor to row 12, through row 12 to the next jumper, from this jumper over to the negative lead of the meter. The current will then flow through the meter and through the positive lead that's connected to the positive bus, through the positive bus, and out to the power supply. Looks good to me. We're about ready to put some power to it. But before I hook up my leads to the power supply, I'm going to turn it on and set the voltage where I want. Let's say 3 volts. Looks about right. Now I hope at least some of your ears perked up, because now we have enough information to calculate what the current flowing through this circuit should be. Got your pencil and paper handy? Ohm's law states that the current should be equal to the voltage divided by the resistance. So that's 3 volts divided by, and remember that we said this 220 ohm resistor is actually 217.4 ohms. So 3 volts divided by 217.4 is 0.0137 amperes, or 13.7 milliamperes. Let's see what happens when we turn it on. Drum roll, please. So, 12.96 milliamperes. Not quite what we expected, is it? While we have this hooked up, let's check the voltage across the resistor. Since our supply voltage is 3 volts and the resistor is the only device in the circuit, we should get 3 volts. But as you can see, the reading on the meter is a little low. Why is that? Remember when I said that the breadboard is not a precision piece of equipment? It looks like there may be some slight voltage drop in the metal strips in the board, or maybe even in the wires themselves. For this simple circuit, I kind of took the long way around. Let's eliminate the board and the wires and then measure and see what we get. That's much closer to our input voltage. Don't let these inconsistencies scare you. Once you realize that seeing the exact values come up on your multimeter is not that critical, you'll be able to digest this stuff a little more easily. Let's try the 330 ohm resistor, which is actually 324.1 ohms. 3 volts divided by 324.1 ohms is 0.0092 amperes, or 9.2 milliamperes. And turn on the power. At 8.83 milliamperes. Looks like we fell short again. Let's verify our voltage, and for the sake of brevity, I'm going to just measure it here with everything in the breadboard. Okay, about 3 volts. That's what we expected. And how about this 1000 ohm resistor, which is actually 988 ohms? 2.97 milliamps. About the same result. And the voltage? Same as well, about 3 volts. We seem to have fallen slightly short of each expected outcome. Knowing that the equipment is not top of the line is a valid explanation. So how much are we off in the grand scheme of things? The measured values all seem to differ from the calculated values by a similar margin. Let's do a little easy math and find out exactly how far off we are. It looks like on average we're at 96% of calculated value. That's fairly close. Years ago there was a physicist by the name of Julius Sumner Miller. He hosted a show on PBS called Why Is It So?, where he spoke of the basic principles of physics. I used to watch him frequently, and one of the things he used to say that has stuck with me through the years is this: the experiment did not fail. We failed the experiment. Can you name something in this experiment other than the breadboard that may have caused our measurements to run askew? Professor Miller was a lot of fun to watch, and I urge you to check out some recordings of his show. I'll post a link where you can find them in the description of this video. I hate to tell you this, folks, but it looks like there's going to be a part 3. I honestly didn't think that 18 pages of script would yield over 30 minutes of video. But there's a little more that I want to demonstrate, so join me next time for the exciting and dramatic conclusion to resistance and resistors. I'm Mo Fogarty, and I'll see you on the next Bad Mofo Show.